Okay, welcome everyone. So our speaker today is Vjekoslav Kovac from the University of Zagreb, and he's going to talk about lower bounds for the LP norms of some Fourier multipliers.
Thank you, Polona, for the introduction and for inviting me to speak here. It is a pleasure. So my title is Lower Bounds for some LP norms of Fourier multipliers. The talk will consist of roughly of two parts. The first half is joint work with Andrea Carbonaro from Genova and Oliver Dragičević from Ljubljana. And the second part is joint work with Alexander Bulj, who is a graduate student here in Zagreb. All right, so the topic is lower estimates. So what do we mean by lower estimates here? Well, so suppose that you have some operator, which could be a singular integral or some other Fourier multiplier. We'll specify this a bit later, and that you prove some nice upper bounds of this form. You can phrase the bound as a certain upper bound on this number, which is the operator norm of your operator on some LP space, right? And then you immediately start wondering how good or how sharp your upper bound is. Well, quite tautologically, the only way that you can prove sharpness of your bound is to prove certain lower bounds, right? Lower bounds for the same quantity. So, of course, it is natural to try to prove a bound like this one. And what is this bound? Well, just let me clarify. The operator norm is defined as a certain supremum, right, of the output functions t acting on your input function f, as f ranges over all functions that have LP norm equal to 1, right? So strictly speaking, this is a certain supremum, and you're proving a lower bound for that supremum, right? It sounds like something quite easy because you only have to construct a certain example, right? You just plug in your favorite function and try to compute the output and measure it in the LP norm sense, right? So it sounds like something quite easy and quite straightforward. And of course, in most papers that you encounter, the authors usually say, well, here is what you plug in, verify it by yourself, and you're done, right? Well, the only thing is actually that your operator could be quite complicated, or maybe it depends on certain additional parameters and you want to track down sharp asymptotics in terms of those other parameters. So the actual setting is that we have a group of operators. Well, I'm calling it a one parameter group, but strictly speaking, you're just starting with your favorite operator t and raising it to either integer or real powers, right? So depending on the operator, right? Of course, if your operator is merely invertible, then actually integer powers make sense, right? It might not be automatic that real powers make sense too, that you can apply that kind of functional calculus to your operator, but in many instances, actually, you can. Okay, so this lambda is either an integer or a real number, and you start raising your operator to those powers. And then you might start wondering about some sharp asymptotics of operator norms. A typical situation is with singular integrals, right? So the whole Calderon-Zygmunt theory that has been developed since the 1960s is of that kind, right? You You know from this very general and rich theory that many operators immediately and quite automatically extend from L2 to all LP spaces for P is strictly greater than 1. You can even say about some dependence of their norms on P and so on. But it's not so immediate what happens to the powers. So actually, these are the estimates that we want to study. And in this talk, we will say that an estimate is sharp if it gives sharp asymptotics simultaneously in the exponent lambda and in the Lebesgue exponent P. So it means actually we have an upper bound and a lower bound of the same form, where this kappa of lambda P is some very concrete explicit function, while these constants only depend on the operator and not on nothing else. And we will write such bounds in this way, that this operator norm is comparable to this quantity kappa in terms of expressed in terms of lambda and P. All right, so if you're still with me and you still haven't proclaimed this talk to be entirely trivial, because you might still believe that bounding operator norms from below should be something rather easy, then I'll try to teach you a few tricks on how to do this when the operator in question is somewhat complicated, and when the aforementioned asymptotics has been an open question for a while. It turns out that the techniques that we will see are actually tailored to give something even more. They actually care maybe even too much about the exact constants. So in many cases, we will actually see a very concrete number appearing here. So actually, it might be helpful when you actually wonder about the exact norm of a power of a certain multiplier, let's say. However, I'm not gonna ever say that this is the exact norm, because the upper bounds, the exact upper bounds are rarely available. I mean, a prototypical example will be the Alfors-Berling operator. You can make conjectures about lower bounds, but if you cannot match them with an exact upper bound, then you never know if these are sharp indeed. Okay, and since this talk will be primarily on lower estimates, I'll only spend a few words on the upper estimates. Well, for all operators that we will see in this talk, for everything that we're concerned with, the following quite general result applies. So if you have a singular integral defined as a convolution with a homogeneous kernel and translation invariant, of course, then there is a very, very nice series of results that all bound the weak L1 norm of the singular integral in terms of the kernel restricted to the unit sphere. So for us, it will be even sufficient to control the L2 norm of the kernel on the sphere. But there are even sharper results that show that it's sufficient to have L log L norm of the kernel, and it is known since Calderon and Zygmunt that nothing smaller than an L log L is sufficient. So there's a series of results starting with Christ and Rubio and Francia, and in several lower dimensions, then by Hoffman in 2D, then finally by Seger, who proved this very strong result in all dimensions and requiring only the L log L control of the kernel. Then Tao generalized this a bit further and so on. So this series of results is a series of results on so-called rough singular integrals, because they only assume some size estimates on the kernel. they don't assume any smoothness, and they do not depend quantitatively on any smoothness estimates of the kernel. The kernels that we're interested in are smooth. That's out of question. But the thing is, when you start differentiating the kernels, then you would get, and if your estimates depended on the derivatives too, you would get much worse dependence in the quantitative sense. So that's why this is useful, because you can bound this merely by the size of the kernel. And combining this weak L1 bound with usually or easy or automatic L2 bound and real interpolation, it often gives you sharp LP estimates. So that's about the upper bounds. And as I said, the upper bounds are easy modulo those beautiful general results. So it turns out that we only need to discuss the lower estimates. So even though we will state the upper estimates too, of course, we'll say a few words on the asymptotics in each of the particular cases, we will concentrate on proving the lower estimates only. And here I start with the first example, and then we'll try to generalize what we've learned from this example. So in the first example, we consider powers of the so-called complex RIESZ transform. So what is the complex RIESZ transform? It is a two-dimensional single integral. So it is this kind of combination of the two RIESZ transforms that are defined in the most standard way, in the standard normalization, R2 plus I times R1. For some reason, this is actually the natural definition, even though you can, of course, maybe permute the two or consider some other normalizations. If you define it this way, then it is actually a very nice Fourier multiplier whose symbol is simply z bar over the absolute value of z, or you can call it zeta bar over the absolute value of zeta. So the kth power of this operator, well, also has a very simple symbol. It's just the symbol that I mentioned, raised to the power k, nothing else. So in this particular case, in the case of this operator r to the k, you can even compute the kernels. And the kernels are also quite explicit. They look somewhat similar. And what pops out is also some linear dependence on the absolute value of the exponent k. And there are some signs and so on. But in short, this is actually quite explicit, and you can still work with this. So why is the complex RIESZ transform interesting? Well, first, the square of R is the well-known Alfors-Berling operator, because if you square this symbol, you get zeta bar over zeta, which is just the symbol of the Alfors-Berling operator. But it turns out that actually this complex RIESZ transform is even more important, because IWANIEC and Martin, in their paper from 1996, they studied a bunch of nice higher dimensional objects. They even have like a whole series of results, like 7 or 8 of them, that express bounds of certain higher dimensional singular integrals, all in terms of the norms of powers of the complex RIESZ transform. So they have a series of results that are explicit up to the fact that you see this quantity appearing in many of them. Which means that actually, well, it's not a secret, but what they do is mostly using some really clever tricks, and starting with a complex RIESZ transform, and then inventing some sort of complex method of rotations to handle higher dimensional objects. Then they have some nice complexification tricks and tensoring tricks and so on. But it turns out, and they say it explicitly in their paper, all that is still left unknown, the thing that is still unclarified is the precise asymptotics of these numbers, right? So they kind of implicitly ask about the actual asymptotics of these numbers. So here P is, of course, a number between 1 and infinity. And here and also throughout the rest of the talk, Q will be the conjugate exponents, and P star will be the greater of the two numbers, P or its conjugate. So Dragicevich, PETERMICHL, and VOLBERG have already clarified the case of even powers, because they were primarily interested in powers of the Alfors-Berling operator, and they have the sharp asymptotics up to some absolute constants, right? So this is comparable up to some absolute constants that are independent of K or P. I'll explain this quantity a bit later. And Dragicevich also commented on that a bit further. He even has like a very sharp, he has a very concrete lower bound for the even powers. It turns out that in order to prove this lower bound, they only needed to consider certain truncations of this very special function, right? Absolute value of z raised to the power -2 over p. However, it turns out that this function is not in the LP space. If it was, it would be very easy, just plug it in and compute the norm. But it turns out that it isn't. So it turns that you have to consider certain truncations in any sense that you wish, and then plug in those truncations, which now make sense. I'll explain in a moment why this is not so easy as it might seem. Well, certainly the case of even exponents k is easier, because r squared is just this nice local operator. But in the case of odd numbers k, you only have an expression like this one, which is still allows you to work with it, but it's not a local operator, and it's not something that you can just have in completely explicit sense. So what we did last year is that we confirmed the same conjectured asymptotics for the odd powers of the complex RIESZ transform. So this is the very same expression that you saw stated in a paper by Dragicevich, PETERMICHL, and VOLBERG. For some reason, I like writing it this way. So this 1 - 2 over p star is the same as 2 times the distance between 1/2 and 1 over p. It will be useful for higher dimension analogies, because this 2 kind of reminds us of 2 dimensions, because we work in 2 dimensions here. And this p star -1 is certainly comparable to p star up to constants, right? So you could write it simple like p star, but it turns out also that it's more elegant to write it as p star -1, because there is a p star -1 conjecture, right, on the exact norm of the Alfors-Berling operator. And because those operators are unitary on L2, so when p equals 2, the right-hand side above is actually equal to 1. So it's kind of nice to have the exact equality for p equals 2. We also have the exact asymptotics of the weak L1 bound. We also have something, we could also say something about the L infinity to be a BMO bound, but then we're not sharp. We're losing a logarithm here or there, so I'm not going to discuss this much. And in the paper, actually, we give 3 different proofs of the lower estimate, which, as I said, is the only thing that is essentially left to do, right? Because the upper estimate is quite general by this very general principle. Now I come back to the natural question: why didn't we just plug in this almost or approximate extremizer, truncated perhaps? Well, I mean, kind of did. The first proof proceeds precisely that way. but it turns out to be by far the most difficult proof. You can do that because you have an explicit expression for the kernel, but it's not so easy because the kernel has very subtle cancellation, and you have to be very careful taking this cancellation into account. And yeah, well, you can do it, but then it turns out to be some 11, 12 pages, even if you're cheating with super small font and negligible margins. But the other two proofs actually give a very concrete constant, right? So we actually are able to conjecture, we dare to conjecture what the exact norm could be. So this would be a sort of generalized IWANIEC's conjecture, because the original IWANIEC's conjecture is just for k equals 2, and then here you see just p star minus 1, or p minus 1 if p is greater than 2. It turns out that Dragicevich also conjectured the same for the case of even k, but in the case of even k, this still simplifies a bit, and you don't really have to write it down in terms of the 4 gamma functions. But about this expression, you cannot really say much. You can write it in terms of hypergeometric functions and such, but this doesn't help. Okay. Let me say a few words about the proof, and then we'll see what could be the somewhat general idea or somewhat general principle. I'm explaining one of the 3 proofs. It's the second proof. No wonder the paper has 3 authors, so obviously each author has their own preference, their own favorite proof. This is my favorite proof. So we're plugging in 2 functions, but we want to make sure that actually rk applied to the first function equals the second one. The functions will depend on quite a few parameters. They will depend, at least the first function will depend on the exponent k. They both depend on p, and they will also depend on a certain truncation parameter epsilon. Now, the easiest way to define these 2 functions is on the Fourier side, right? Because rk is a Fourier multiplier with a very nice symbol. So we define them this way. This G is a certain superposition of Gaussian functions, and then f hat is just what it needs to be in order to have this equality, right? So now when you multiply this guy with zeta bar over absolute value of zeta raised to the power k, you just kill this twist and you end up having g hat, of course. So if you integrate it from 0 to infinity, you would get a constant multiple of zeta absolute value raised to -2 over q. And similarly for the function f hat, right? So these are certain truncations, but truncations on the Fourier side. It turns out to be more elegant way of doing things. So the first one, the first function, not truncated, just considered as a local integrable function, has the distributional Fourier transform equal to absolute value of z raised to -2 over p. And similarly for the second function. So actually, this is not far from what we expected, because we expected those approximate extremizers to be certain truncations of these functions, right? So those functions, they still appear somehow. It's just that we're truncating things on the Fourier side. So what do we do now? Well, now this is the messy part. You still have to estimate some LP norms, right? So now you have to compute inverse Fourier transforms. Well, the inverse Fourier transforms can be computed somewhat explicitly. They're not terribly nice, but it's doable just because Gaussians have explicit Fourier transforms. So at least if nothing else, I can still have my function written as a superposition of Gaussians. But when you change variables and such, you see that actually you're getting an expression like this one. One more time, I'm just saying, if you let epsilon go to 0, this converges to very concrete constants. It turns out to be some particular gamma function. And again, you get a constant multiple of this function. So there are no surprises. But you need to be more quantitative. You need to estimate the error in terms of epsilon. So it turns out that you can do it. You can estimate the LP norm of this function as there is some main term and there is an error which is bounded, which stays bounded as epsilon goes to 0. This quantity here is just this integral that is left after this is replaced ideally as with the constant, with the gamma function. And this integral turns out to be computable. You can compute it explicitly as this messy expression, again, in terms of gamma functions. And you already see how gamma functions appear in the expressions. And you do the same for the function g. Again, you have some main term and you have some error. So what do you do? The operator norm is bounded from below by what you get from plugging in f acting by r to the k, computing the norm of the output and dividing by the norm of the input and letting epsilon go to 0. And what you get on the right side, this limit just equals what we had, the constants that we saw, this 4-tuple product or the quotient of the products of two gamma functions. And that's it. Well, yeah. Did we learn anything from this? Well, maybe. We'll see. So here are a few words on the generalization. A generalization, now I'll speed up just a little bit. Now, a generalization will try to mimic what we just saw. The generalization will try to work in higher dimensions, but it will be also slightly more general even in 2D, because it will also answer a question in 2 dimensions. So a spherical harmonic, I need to remind you, of degree j is simply a restriction to the unit sphere of a harmonic homogeneous polynomial in n variables of degree j. So in 2 dimensions, a prototypical example would be the following polynomial, written as a function of a single complex variable. It's not only a harmonic, it's even holomorphic. So it's trivial harmonic too. And when you restrict it to the unit sphere, you get these guys, which are the well-known building blocks for the Fourier series expansion. So why are they important for us for constructing lower bounds? Because of this result that is stated in the book by Stein and Weiss, but it might be older. Yeah, I wouldn't be surprised. It is that if y is a spherical harmonic of degree j, then when you take a look at this local integrable function, again, you see the same RIESZ potential power as before, but then you have a twist, which is not just a simple power, it's a twist with this spherical harmonic evaluated at x over the modulus of x. Then the Fourier transform of this distribution is just a distribution of the same type, just with a different the power. And some constant pops out, and this constant is written down there. This even makes sense in the endpoint case, but p is equal to 1, but then this function is no longer locally integrable, but so you have to understand this in the sense of principal value distribution, and then the same formula holds. So those constants appear already in the book of Stein and Weiss. Let's regard them as something standard. Okay, so here's a general theorem that Alexander and I could do. So start with an exponent p and take a symbol m to be just any bounded homogeneous measurable function. So you don't need much. And take a sequence yj so that each yj is a spherical harmonic of degree j. And these are quite technical assumptions. You want the series of these spherical harmonics to converge in the LQ norm on the sphere. So this is something stronger than requiring this just to converge in L2, because on the sphere, LQ norms are bigger, and Q is greater than 2 in our case. And this weighted sum with signs inserted converges in the L2 sense. Let me remind you that spherical harmonics of different degrees are mutually orthogonal. So this is an orthogonal series. But the first series should be trickier because it's not in the Hilbert space, and orthogonality does not make sense anymore. And then we have a very concrete lower bound for the multiplier operator associated with the symbol m. We have a very concrete lower bound with some constant. Those are the same constants that you saw on the previous slides. This is the measure of the unit sphere. And these are the quotients obtained by, you see, pairing the symbol with this function f, v, defined as the sum of this series, and divided by the norm of the function u, defined as the sum of the former series. It turns out that this constant is, you can find it asymptotics easily. It's at least some constant depending on n times q minus 1. And here is where you get this p star minus 1 dependence. You get it from here. And also this even holds in the endpoint case, right? The weak L1 norm is bounded from below by this same quantity, just take q to be equal to infinity. So in short, we have to have some clever guess for the two spherical functions u and v, whose expansions into spherical harmonics are compatible. They somehow match in this sense. They're proportional. And we have to choose u and v wisely, and we plug them in and just compute those things. I mean, compute or estimate anyhow you can. It turns out that you might suspect that maybe the best guess would be to choose v equal to m and then compute u from there. I mean, whatever it turns out to be. I don't claim that this is optimal, even though this is certainly optimal in some cases. But this approach gives you some flexibility. Because these are usually some horrible things to compute or even estimate, then choose whatever you can deal with. Try to find u and v that are manageable, right? And hope that they're not very far from the optimal choices. So within constants, that they still give you the sharp asymptotics. So what's the proof of this general result? It's actually somewhat easy. We just have to quantify this Stein and Weiss formula that I just mentioned before. We have to quantify it in the following sense, that for p, epsilon, and any spherical harmonic, you can find a Schwartz function that approximates those spatial truncations of the first function quite well, right? And so that the Fourier transform of this Schwartz function approximates the truncations of the second local integrable function in the LQ norm. And the errors turn out to be independent of epsilon, but all that we need is actually that of a smaller order of magnitude in terms of epsilon than those main terms, right? So I don't want to let this epsilon go to 0 too quickly, right? So I want to work with some truncations, but it turns out that it's more convenient, of course, to have a single function for which you have exact Fourier transform mapping, because you're acting as if this truncation had its Fourier transform equal to precisely this truncation. This is certainly not the case, but it is the case up to errors of smaller order, right? And how to do this? Well, I don't claim this is the only possible way to do that, but it's very convenient to do it by expressing those guys as superpositions of Gaussians. And actually, this is what Stein and Weiss do in their book. This trick has been exploited a lot. So this barely counts as an original result. I wouldn't even dare to say that it's 100% original, even though I haven't seen it formulated that in that exact way. So what do we do? What do we do? We choose the first Schwartz function f so that it doesn't differ much from this truncation, right? And that its Fourier transfer doesn't differ much from this truncation. Choose the function g so that it doesn't differ much from this truncation, and so that its Fourier transfer does not differ much from this truncation. So those weights and signs appear just, they have to appear because, as we said, they need to appear because they will appear in the limit when epsilon goes to 0. And now plug those functions f and g inside, and you are done, right? Plug them inside, use the Plancherel's theorem. Write this in polar coordinates, just as integration on the sphere, and because integration in the radial direction is trivial. And then, of course, you have those expressions, and you have errors of smaller order. Then first let epsilon go to 0, and only then let the number of terms go to infinity, and you get the lower bound that we wanted. And that's about it. The lower bound for the weak L1 norm is not difficult. It's actually obtained from here. This is a trick used already by Dragicevich, PETERMICHL, and VOLBERG in their paper, simply because you have a very concrete constant here. And you know that the real interpolation only makes constants better in the interior. You could just use Marcinkiewicz interpolation and then let p go to 1. And in the limit, you get the weak L1 bound. It's actually very easy. It's very easy if you have a very concrete bound here. Something that I hope to be optimal. And so now, in the remaining time, I will show you 2 applications, right? 2 applications to the questions that at least someone was interested in. So the first application, besides the complex RIESZ transform, but the complex RIESZ transform came before, right? It was actually inspiring and inspired this more general setting and more general ideas. The first application is concerned with symbols of this form. So these are just symbols of the form e to the I lambda, when lambda is some large real parameter times a certain phase. And the phase is simply some smooth real valued function on a sphere. And just by definition, this symbol is again homogeneous. So it's homogeneous and clearly unimodular. But let me comment immediately that the complex RIESZ transform does not belong here. The complex RIESZ transform has a certain twist, but it's not of this form. You don't have a smooth phase in the exponent, right? You cannot find a nice 2π periodic function on the unit circle that gives you the RIESZ transform symbol. You cannot even find a continuous phase with this property. And then again, you consider the Fourier multiplier with this symbol, and that's it. And naturally, you start wondering about the asymptotics of the LP norms of those Fourier multipliers. So supposedly, Vladimir MAZ'YA was interested in this question. It arose quite naturally from his early work on the Fourier multipliers back in the 1970s. But then he phrased it or rephrased it and formulated explicitly on his list of 75 open problems in analysis and PDEs in 2018. So this was problem 15 on his list. So the problem asks to prove or disprove this upper bound, right? So that those LP norms grow like this particular power of lambda. In the exponent, you should have n-1 times this distance between 1 over p and 1/2. Let me first say that this conjecture is quite reasonable at the first sight, because in 1D, when n equals 1, all these operators are trivially bounded linear combinations of the identity and the Hilbert transform. So they clearly satisfy uniform bound independent of the power lambda. In higher dimensions, just any standard formulation of the Hermann-Michel theorem easily gives an upper bound that in exponent has the same quantity times maybe n plus 2 or something else. If you consider slightly sharper versions of the Michel multiplier theorem, you might lower this easily to n plus epsilon or something like that. But it's not really clear if you can lower it down to n minus 1. Well, it turns out that it has been overlooked. The paper by Dragicevich, PETERMICHL, and VOLBERG implicitly disproved this bound in 2 dimensions. I'll come back to this a bit later, but it turns out that in 2D, this can be found in this paper by Dragicevich, PETERMICHL, and VOLBERG. But this is not the main result of this paper, so it's understandable that this could have been overlooked. However, it is still interesting to maybe ask about the higher dimensions, or maybe ask about the precise power, precise asymptotics, or even better, to ask about the sharp asymptotics. And by sharp, I mean both in the exponent p and in the power lambda of those operator norms. So we have the following result. So in any dimension to an up for any exponent p and any parameter lambda, we have upper bounds of this form for all smooth phases, right? The upper bounds are always from something similar to what you saw that happens for the complex RIESZ transform. You again have p star minus 1 times this parameter lambda raised to the power n times 1 over p minus 1 over 2 absolute value. So this is the distance between 1/2 and 1 over p. And again, you have a compatible upper weak L1 bound. And more interestingly, from below, in all even dimensions, we could prove the following. We could find a phase that actually attains this worst possible asymptotics, right? There is a phase so that all integer powers, well, we kind of needed integer powers because it was convenient in the proof, so that all integer powers actually of this operator t actually have the worst possible growth of the LP norms. In particular, you see that the MAZ'YA'S problem has a negative answer in all even dimensions, and just because in the conjecture you saw n minus 1 here, but it turns out that you cannot beat this exponent n times this expression at all, and this is actually the sharp exponent, and even better, this is actually the sharp asymptotics. Quite easily, you could use the group property and extend this from integer powers to the real powers. But then this could mess up these sharp asymptotics in P, so I'm not formulating it that way. Let's stick to the integer powers from below. It turns out that this is probably also sharp asymptotics in odd dimensions too. This follows from independent subsequent work of others. So it turns out that I certainly need to mention independent work of Dmitry Stolyarov, who independently showed some upper and lower estimates for MAZ'YA'S problem. So we were not aware of each other's progress or work, and Dmitry uploaded his preprint just a day after we did it. Here is what he proved. He proves an upper bound of this form, which is again sharp in the exponent, but not necessarily sharp. It turns out it's not sharp in the exponent p. So he didn't really care about sharp constant in p, and he only misses the weak L1 endpoint. But once again, he uses as a black box another result of Sager. So, as I said, it turns out that the upper bounds follow from readily available results in the literature, right? But it's actually a different proof. What we were doing, we're estimating the kernel, and what he's doing, he's just using an endpoint result of Seger and using some smarter interpolation than just MAZ'YA'S interpolation here. He also proves lower estimates in all dimensions. But one more time, it's actually not really clear if we can anyhow use his ideas to obtain estimates that are sharp in the exponent P2. So his proof seems to be more efficient regarding the dimensions, but misses the sharp asymptotics in P. So how do we proceed? Of course, we need to plug in something to our general theorem. So what do we plug in? Well, it would be ideal if our symbol was just this function, just a product of certain two-dimensional rotations, or a product of rotations in two-dimensional planes. But this is horrible. This as a symbol would be horrible because this is too singular, right? It's actually singular on many two-dimensional planes, and it's not even clear that this would give like a bounded multiplier or anything. It turns out that we're not using this as an approximation of the symbol. We're just using this to get the correct spherical harmonics. So we expand this function into spherical harmonics, and then construct our functions u and v from those spherical harmonics, right? We insert the correct, we insert the certain weights. They're not, there's no canonical choice of weights, but there are some weights that we can handle. At least we have some explicit expression, something that we can compute. And then now the main difficulty is moved to merely showing that this function uk, defined as a series of spherical harmonics, has the correct asymptotics of the L infinity norm. It turns out that all its Lebesgue norms are mutually comparable, and that all have the same order of growth, or decay actually. They all decay like k to the negative power n over 2. And how is this shown? Well, this is the messy part of the paper. We have somewhat explicit expression, right, of those functions, but in terms of integrals of Bessel functions, and you have a multiple product of these integrals, and you integrate this over all scales. How do you obtain things like that? Again, superposition of Gaussians enable you to at least have something somewhat explicit, but not entirely explicit, of course. And once you can bound this from above, or just the denominator from above, you're pretty much done. The numerator is easy because you have orthogonal series, and you can somehow bound it from below. And turns out you plug in to the expression that we saw in our general theorem, and we're done. We get the correct asymptotics. So just to remind you, the constant in terms of p that you saw comes from the other part. You saw it you saw it as another factor in the general theorem. This is the part that deals the asymptotics in terms of the exponent k. And just in the remaining like 2 or 3 minutes, let me say a few words about the second application. This is a very, very concrete symbol, a very concrete phase function. So if you took the phase to be simply the projection of the whole unit sphere onto the first coordinate, just take the first coordinate of every point on the sphere, then you get a very special Fourier multiplier. This group of multipliers is sometimes called the RIESZ group, or some people call it the Poincaré RIESZ group, or the RIESZ-Sobolev group, simply because its infinitesimal generator is the negative of the RIESZ transform. Right? You see it from here. Expand this. This is just the derivative at lambda equals 0. In 2 dimensions, it's particularly simple. You just have this phase, and simple is very explicit. You see this cosine in the exponent, and also the Fourier multiplier is reasonably explicit. So Dragicevich, PETERMICHL, and VOLBERG actually studied asymptotics and in the sense that we care about, asymptotics that is sharp simultaneously in P and K of these operators. And they were able to prove the desired, the same optimal upper bound, but for the lower bound, they miss by a power of by a delta power of K. Right, so instead of having this sharp exponent, they have exponent minus delta, and then of course the constant also blows up as delta approaches 0. But already this lower bound that they prove in their paper, already this lower bound disproves MAZ'YA'S conjecture in 2 dimensions, right? Because MAZ'YA'S conjecture had 1 here in 2 dimensions. Oh, if you take delta appropriately small, you beat this bound and you're done. However, Dragicevich, PETERMICHL, and VOLBERG explicitly ask in their paper if one can remove this delta, right? Can you have like a sharp asymptotics without this delta? Because they suspected that this is doable, and this is what we actually achieve here. So we show that the asymptotics is just as you suspect, right? This is the sharp asymptotics. As you had in the MAZ'YA'S problem, but again, this is a very special choice of the phase, right? We didn't say anything about this particular phase before. So how do you prove this? Very quickly, you expand the symbol into the Fourier series, and it turns out that the coefficients are again certain Bessel functions of the first kind. So from this identity, you can also arrive at very nice identities for the Bessel functions. Just take the real parts, so let's say, of both sides, you get this identity. Then you shift a little bit in phi, you get the other identity, and so on. So it turns out that it's a clever choice to use this as a function u. So it's cosine of lambda times sine of phi minus the zeroth Bessel function of lambda, just because here you see an explicit expansion of this difference into the Fourier series, right? And then take v to be what it has to be, right? Just you have to put those appropriate weights and signs that are dictated by this connection between u and v in the general theorem, and plug it in. Right, again, in this expression, plug both u and v from the previous slide. And the numerator, now you need to play a little bit with Bessel functions, just because this orthogonal sum leads you to some inner product, and this inner product turns out to be actually this weighted sum of Bessel functions of higher order. So you actually have to work a little bit, but not too much, on estimating this from below. While estimating the denominator from above is trivial, because this is clearly a bounded function. It's a very concrete function, right? It was a cosine of something, so on. So it's clearly bounded from below, from above. And actually, that's it. That was the second application, and I'm done. So here you see 2 references. Both papers are on the archive if you want to see more details about the actual proofs. Thank you very much.